Hello, and once again, welcome to the fifth lecture on stereoisomerism. Am I audible, Rudra?
Yes, sir.
Good evening, sir.
You are late. So, last time we had completed all the aspects of optical isomerism involving chiral centers: one, two, more, symmetrical, unsymmetrical, having mesoforms, having no mesoforms. The only thing we are now living for maybe coming classes discussion, that is optical isomerism in presence of chiral axis. The optical activity of substituted allenes, cumulated dienes, substituted alkylidenes, alkylidene, cyclohexane, very similar to allenes, and also spiranes, substituted spiranes. And we will be dragging that to conformational enantiotropism, a very important topic is isomerism. The optical isomerism in substituted biphenyls, and they are conformational isomers and as well as enantiomers. They are separable because the hindrance to rotation is quite high, and so I deliberately am leaving the optical activity due to chiral axis and the conformational enantiotropism after we complete conformational isomerism. So before that, let me share my screen, which I haven't yet. First, we shall be, this is our agenda now, because as I have told you, yesterday I was not happy with Rudra because he will never say a false thing or a lie. Instead, he will feel sorry and apologize. That is his sobriety and humility. That if you have seen my posting, that I have not forgotten after 2 or 3 days of halt, I mean break, I have not forgotten. I am scheduling our program and giving you the links, and you were supposed to interact. Okay, sir, something which you didn't until I sowed my anguish by saying we will not have the class. Then you realized what happened, Rudra.
No, sir.
You didn't really see?
Sir, my sister has
What
seen,
happened? What?
sir, my sister has seen that message and I
I'm not
just
able to hear you. Something has gone wrong with your audio. The moment, I will feel that you are with me just for sake of with me, not as an absolute requirement, then I may feel like stopping the program, as I have already told you before. I have been telling this from time to time that if you are otherwise busy, then you can have only doubts clear session, not a regular session. But you didn't. You wanted a regular session. If that is the case, I told you that you must give me a feeling that you need me. Otherwise, I don't need you. There should be a mutual, reciprocal, interaction, not one-sided. So what happened, Rudra?
sir, actually, I haven't test today and I haven't seen phone yesterday. So, sir,
Oh,
um,
yeah, yes, yes. Then you are telling the truth, no doubt. I will,
uh, so,
I
so
will.
my sister told me about that and I returned the message.
Your sister told about it. You should have told your sister, give me a message on my behalf that yes, okay, sir. Well, oh, you knew it just after I showed my reaction.
Yes, sir, my sister told that you were
Okay, okay,
angry.
okay, okay,
So,
okay, okay. It must be genuine, no doubt. Let us stop further discussion on this point. Enough is enough. Let us now not revise what we did in optical isomerism. Start straightway the EZ isomerism. It was previously called cis-trans isomerism. And also some people call it geometrical isomerism. These are diastereoisomers, as I have already told to you in my introductory classes, that a double bond with different groups, it can be also same AB also, but these two should be different, these two should be different. These two may be same, these two may be same. So these are candidates for showing stereoisomerism, diastereotropism. They are chiral molecules. They are not chiral. As I told you, the molecular plane itself is the mirror plane. So they are not optically active, but they show geometrical isomers. For that, you already know cis and trans. But nowadays, cis and trans is only applicable when the groups are identical. When the groups are identical type, this is cis but twin, you can say people can understand. They will not dispute about it. And if you make a switch at the one of the stereo centers, this is not called a chiral center, stereo center. A chiral center is a stereo center, but not all stereo centers are chiral centers. So just I change this. I switch this, and now you find the geometrical relationship between the identical groups are different, and this is trans. So cis trans terms can be used when at least, you know, can be used when at least one pair of groups are identical. Supposing hydrogen, hydrogen. If the other groups may be different, for example, this is methyl, this is say chlorine. This is hydrogen, hydrogen. In that case also, you can use the term cis and trans because they will also conform to the EZ notations. But the moment you find the groups are different, you should never ever use the term cis and trans. Therefore, cis and trans terms have been obsolete now. Even for butane, we say Z butane for cis and E butane for trans. So this you can call a cis. This will be 1, 2, 3, 1 chloro propene, propanine or simply propene. Now we call it Z. And if you make a switch, any switch, here or there, doesn't matter, not both switches. Both switches will make the stereo centers, then you get the two hydrogens will be coming opposite. So this will be trans or E. Now, how to away from each other, and Z just men close to each other. So EZ notations are given. So each stereo center has two groups assigned their priorities 1 and 2. One and two for one, and 1 dash and 2 dash for the other. If 1 and 1 dash or 2, obviously 1 dash or 2 dash remain on the same side, then it is Z. This is the cis counterpart for simple molecules. And if the higher priority groups or the two lower priority groups lie on the opposite side, then we call it E. So this can be applicable to any, supposing this and this is carboxylic acid and this is methyl. So there E and Z, cis and trans has no meaning at all. And here the same CIP rule will be applied. But 2 times, not for 4 groups. 2 times. For this carbon, this stereo center, this chlorine is number 1, this is number 2. And for this stereo center, carboxyl is number 1 dash and this is 2 dash. Then 1 dash and 1 dash, 1 and 1 dash or 2 and 2 dash, they are remaining on the same side. So we have to give a notation Z. And to be more correct, you, according to the IUPAC naming 1, 2, the starting stereo center will be given this locant 2Z. Then the name. Name will be what? This will be 1, 2, 3. This is 3 chloro,
2 methyl,
2 methyl,
prop 2 enoic acid.
prop 2 enoic acid. 1 oic acid is redundant. You may write or may not write. Punch it 2 enoic acid. But this is in between bracket. You must, I mean, in between parentheses, you must write 2Z. That is the identity indicating that this has another form. Just by switching, you can get another form which is a diastereomer, having different physical properties. That's the beauty. If you just change it here, you will find that the higher priority groups or the lower priority groups, this is 1 dash, going out, I mean, opposite to each other. So this will be 2E, same name. So GIs, geometrical isomers, are diastereomers, as I have already mentioned, and have different physical properties, all boiling point, melting point, and can be very easily separated, very easily separated by many physical methods like fractional distillation, fractional crystallization. Nowadays, they are going for chromatographic separation. So there are several methods to separate because they have different physical properties. Um, and if there are multiple double bonds, you can also have just like multiple, you know, supposing this is methyl hydrogen, this is hydrogen, this is also hydrogen, this is methyl hydrogen. So you have to have two, this is a symmetrical molecule. So there will be one diastereomer less. Just like RS is same as SR. Similarly, ZE and EZ, they are superimposable. So there is no different. But if the molecule is unsymmetrical, this side methyl, this side ethyl, then ZE and EZ, they are different. For example, we start the nomenclature from any side. This will be a 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Hexa 2, 4, dine. So this hexa 2,4-dine, A will come from the pocket, as you know. But before that, you have to mention 2, there is a stereo center, and 4, so 2 something and 4 something bracket. Now see, this number 1 and this is number 2. And for this carbon, the Buddha is number 1 dash and hydrogen is 2 dash. So 1 dash remaining on the same side. So the stereochemistry of the stereo identity of carbon 2 is Z. I mean this double bond, which is represented by the first stereo center. And coming to the first stereo center of the other double bond, here you find that methyl is number 1, hydrogen is number 2, and this Buddha is number 1 dash. This. So that indirectly also you can know hydrogen are the same, they are remaining on the opposite side, means the other two higher priority groups also lie on the opposite side. So this configuration is E. So this is 4E. So 2Z 4E. And if we just switch, you switch this one and this one, so that this will become E, this will become Z. You will find these two are just you make upside down, they are superimposable. But that won't be the case if the structure is unsymmetrical. So, and if you make one switch here, just make one switch here, you have configuration changed. So this remaining, 4 remaining E, but this also goes E. So this will be 2E and 4E. EE. And the name is same. And if you make, keeping the first identity fixed, if you make a change in the last one, look to the first structure. So that 2 was Z. I just change it to H and CH3. So in this case, hydrogen, hydrogen or the Buddha, Buddha, same, this is 2Z. And here also hydrogen, hydrogen, same. Hydrogen will be the identifier. So this will be also 4Z. So these are the thing, but 2Z 4E is same as 2E 4Z. They are superimposable for symmetrical dyne, unconjugated dyne. I mean, non-cumulative dyne. They are conjugated dyne. But if unsymmetrical structure like this one, here there is Me, and here it is Et or something else, chlorine or whatever. I'm saying Et. So according to nomenclature, you have to go this way. 1, 2 में आ जाता है डबल बॉन्ड, यहाँ 3 में आता. So इसलिए 1, 2, 3, 4, 5, 6, 7. It is heptadiene, hepta 2, 4 diene. So you have to have a perfect identity. So hydrogen, hydrogen, same side. Look to the hydrogen, it will be better. So this will be 2Z. And look to the hydrogen on their opposite side. This will be 4E. And this will be hepta 2, 4 diene. And I'm not changing. You go change one by one, one by one. If you change this one, you get 2E, 4E. Keeping this in fixed, if you change this, you get a 2E, 4Z. These two are different. They are not same. And keeping again this fixed, you change this. This will be 2Z, 4Z. So there are 4 GIs or diastereomers in this case. Just like, meso, the presence of a meso one was making the number of total optical isomers less than 1. I mean, and it's not 4. If the molecule is unsymmetrical, no plane of symmetry, 2 to the power 2, 4. 2 pairs of enantiomers. But meso makes only 1 pair of enantiomers and 1 meso. But here we don't talk about optical activity. We talk about diastereomers, no doubt, but we are having 4 GIs here. ZZ, ZZ in practice, ZZ, EE, ZE, EZ. They are different, unsymmetrical. All are diastereomers of each other. There is no question of any mirror image isomerism. They are achiral molecules, so nothing to talk about optical isomerism. Hi, those who are watching from the YouTube, hi. And if you have some patience, you continue, we'll be having a very long session today. Because we have to finish within another 2 sessions. This is the 5th one. Another 2 sessions we have to complete. And I will just throw upon you the entire set of questions which were asked in the previous IIT Advanced as well as JEE Mains and JEE Advanced. So you will be able to answer any one of them involving only stereoisomerism, not geosim. Well, you have a rule. I just oh well, in our agenda that we made, just I'm making down what we'll be doing today. My plan is EZ isomerism, conformational isomerism, then immediately of acyclic compounds. These two, that will be huge. And then we are left with the optical isomerism involving chiral axis. And in that, the conformational enantiotropism. That is included in chiral axis. But an additional thing you will learn that they are not only chiral, optical active, but also they are conformers. They are conformers, conformational isomers. Well, the no bond breaking, no bond breaking is required to convert one such enantiomer to the other enantiomer. Very peculiarly, they are mirror images of each other, and they are also can be converted one to the other by just rotating a single bond about a single bond. Not in the other case, in all other cases, in the first category of having chiral centers, second category of having chiral axis, we have to switch. Unless you make a switch, bond breaking, bond making, remaking, you can't get the other enantiomer. But here is the case, that is why I will discuss it separately. And then we are left with the configuration versus conformation. As I used to say, a wedding ceremony between configuration and conformation. And then the stereoisomerism of cyclic compounds. Cyclopentane substituted cyclopropane, and there you will encounter with all types of symmetry elements like center of symmetry, like C2, C3. You know the presence of a CN axis will make it chiral, whether it is due to presence of chiral centers, that is sp3 hybrid atom, and also, or it is sp2 but it is three-dimensional molecule, not a planar molecule. sp2, surprisingly, it is not a planar molecule, but 3D molecule, and that is chiral due to presence of a chiral axis. We will be knowing that. And then I forgot to tell you that optical isomerism in nitrogen, phosphorus, oxygen, sulfur compounds. These are sp3, which I have left. I should have discussed that. There is a very little discussion because the chiral carbon atoms are so dominant in that category that I forgot to talk about the chiral nitrogen, chiral phosphorus. You must know about chiral sulfur, chiral oxygen, sp3. These are centers. That's it. And then the conformation of cyclohexane and cyclic compounds. So we have to go a long way, and therefore I will not budge to or concede any show any laxity or some relaxation. We'll be going very fast. Now coming to yes, I will show you. There is also interesting rules, just like we had rules. You see, this molecule, we have already discussed that, there is nothing so to waste time. The same CIP rule will be applicable. This is isobutyl, this is N-propyl, which is senior. This is chloromethyl. In this stereo center, chloromethyl, chloro is directly bonded to the first carbon, but bromine is miles away. So this is 1, this is 2, this is 1 dash, this is 2 dash. So 1 and 1 dash remaining on the same side, the configuration will be Z. So I have given so many examples which you can now see there are two double bonds here. You have to identify because this is a stereo center. Hydrogen and Buddha, they are different. Chlorine, hydrogen, they are different. Here also, methyl and chlorine, they are different. Hydrogen and Buddha, they are different. So it will have, an unsymmetrical compound. In all, there will be 4 geometrical isomers. EZ is one, ZD is another, ZZ is the third, EE is the fourth. So this configuration, I have asked the students to identify what is the name, what is the adjective that you can give to this molecule 1,5-dichlorohexa-1,4-dine. So the stereochemistry of 1 is E because chlorine and Buddha or hydrogen remaining on the opposite side. So this is E. And in the case of the fourth one, hydrogen is the lower priority and methyl is the lower priority remaining on the same side, or chlorine is the higher priority and Buddha is the higher priority remaining on the same side. So this is Z. So 1 E and 4 Z and then the name. So which will not. And if there are multiple, I have shown an example where there are 3, 4 double bonds. Each of them is stereoactive. Each of them is stereoactive. I don't say it is, chiral. Stereoactive. So here this is 2E carboxyl is senior and Buddha is senior than methyl. So this 2E and this is hydrogen. Whenever you find hydrogen, this is E, 4E. And then this Buddha and this Buddha, they are on the same. Buddha is senior here and Buddha is senior here. This is the same side. So this is 6Z and 8 hydrogen, the opposite side, 80. Then the name. So I was showing examples where there can be multiple, and the same thing which I've done. And this is, I have told you the molecule is symmetrical. Unsymmetrical, then there will be 4 non-superimposable GIs, ZZ, ZE, EE, and EZ. They are not identical. EZ and ZE, they are not. Unsymmetrical structure like ethyl on one side and methyl on the other side, similar type. But if the two sides are same and it is a symmetrical structure, then ZD is same as EZ. They are superimposable. Just by making upside down, you can superimpose. Now, these things and you just write down here. For unsymmetrical structure, the formula is very similar to that of finding number of optical isomers, optical active isomers 2 to the power n. So number of GIs will be 2 to the power n, where n is the number of stereoactive carbon-carbon double bonds. If the structure is symmetrical, means structurally symmetrical, then there are 2 cases. If n is even, the number of stereoactive double bonds is even, then the formula is something different. 2 to the power n minus 1 plus 2 to the power n by 2 minus 1. If it is odd, then 2 to the n minus 1 is common, but the second term is different. It is n minus 1 by 2, which is n by 2 minus 0.5, half. That is n minus 1 whole by 2. Slightly different. The number will be getting less. Will be a little more because it is the first one is n minus 2 by 2. This is n minus 1 by 2. So the formula will help you in calculating the number of GIs. GIs means geometrical isomers. Over?
Yes, sir.
Yes, sir.
Oh, okay. This thing I will tell you when we will study the optical isomerism having chiral axis. Let me sound you that when there are 2 double bonds in a cumulative position, just one after the other, see, like C double bond C, then C double bond C, and the two groups attached to the terminal carbon atoms are different, then that is a candidate to show optical isomerism due to chiral axis, because that is not a planar molecule. These two substituents will be lying in horizontal plane, supposing, and the two other in the other terminal will be lying in a plane which is perpendicular to this plane. They will be remaining in a vertical plane, because you can understand in what happened in carbon dioxide, sp hybridized. In the middle, it will be sp hybridized. So if this will be using the py for sidewise overlapping, this is pz, so that the two substituents in the terminal carbons will be lying in two perpendicular planes. Once the molecule is not a 2D one, it's a 3D one, and you will find by switching any two of the groups, any two groups at any one of the stereo center, you will get its mirror image. Just make the model, just rotate in your hand, and so keep the two models, you will feel that they are mirror images. They are not superimposable. So this is chiral, doesn't have I, doesn't have sigma, doesn't have Sn, so it is a chiral molecule. But it does have a C2 axis. So not only one C2, there will be multiple C2. So we will not discuss about that. This point group and others, how many elements of symmetry it has, we won't discuss that. I told you that if there is a CN axis, then it is chiral. So, but if there are three double bonds, three cumulative double bonds, five odd number of cumulative double bonds, one after the other, then the molecule becomes planar. Then the molecule, you can yourself, convince yourself from your knowledge of bonding that the second one, this is sp, this is sp. Second sp hybridization, and this is sp2, this is sp2, will make R1, R2, R3, R4 to remain on the same plane. The moment it is planar, it is not optically active, it is not chiral. It is if the two groups are different, just like one double bond, similar will be the case whether it is E or Z. But if there are two cumulative double bonds, it is a three-dimensional molecule. This is in one plane, say R1, R2 in a horizontal plane, R4 and R3 they are in a vertical plane. So just you make a switch and make the model, just rotate, you will find, you visualize the mirror images. These are optical isomers, these are geometrical isomers. So it's now, I would like to just write down here for the sake of our odd number of cumulative double bonds. Cumulative double bond means one after the other. Odd, 3, 5, like that. So this, then this, three double bonds. And it is a planar molecule. These are planar molecules. And if the two groups are different, A, B and PQ, same, so E and Z, the manner you are E and Z isomers, GIs are possible. So this is not a big deal, but let me just here tell you, if there are even number like 2, 4, etc., cumulative double bonds, then the molecule is non-planar. And can be chiral if the groups are different. Due to presence of chiral axis. About this we shall discuss later. So there will be a D and L form. So they are enantiomers. But these are diastereomers, E and Z. These are optically active because they will lie in opposite planes. Supposing this will remain in horizontal plane, this will remain in vertical plane. Maybe same, but this is different, this is different. So this is a vertical plane, and this is a horizontal plane. And this is a, this molecular axis is called the chiral axis. So with respect to the chiral axis, this is dissymmetric. And by switching any of the two, here or here, you will not get a superimposable form. You will get its mirror image. Just you can visualize by manipulating the model in your hand without any. Once you have bond broken and bond remade, then it has become its enantiomer if the two groups are different. If one of the stereocenters have identical groups, it's not a stereocenter then. It is not a chiral molecule. Then the other plane having dissimilar groups, that plane will be the mirror plane, and that makes the molecule symmetrical. It has a sigma plane. You understand what I say?
Yes, sir.
Yes, sir.
So we will be writing that in the proper place, but we are now talking about geometrical isomerism. The physical properties you must know, they are different. And there is no exact rule of thumb. Which one has greater boiling point, which one E has greater boiling point, or Z has greater boiling point. There is no exact rule of thumb. But an approximate rule of thumb can be studied, a rule for symmetrical compounds. I mean, particularly taking butene type of compound and 1,2-dichloroethene type of compound. 1,2-dichloroethene can also show cis and trans. So also butene. These are very symmetrical compounds. It can also have, this is, both are Z, and you can convert it to E by switching at one stereocenter. So for such symmetrical compounds, we have an approximate rule of thumb. Boiling point, Z is greater than E. Melting point, the opposite. I will give you the concrete examples, proof, and everything, because boiling point Z, in Z, the methyl, they are lying on the same side, so van der Waals force will be less. So van der Waals force will be more. So it will boil at a higher temperature. Van der Waals force will be more. They will be having more area. But why melting point of E is more? Because when it is E, then the packing in the solid state will be more profound, more efficient, for which more energy will be required to break the lattice, and therefore E or trans will have a greater melting point than Z. But the boiling point is the opposite. Similarly, the dipole moment, definitely Z is less than E. For example, you take this has an, this vector, they lie at an angle of 60 degree. How much? And the resultant will be quite high. Mu is not 0, but if you take the trans one or the E one, then the two vectors are opposite to each other. They will exactly cancel out if the atoms are same. Had it been chlorine and this bromine, then definitely trans would have some residual dipole moment, but it will be definitely less than the cis Z. So this in case this is 0. So also the case of butene. Cis butene has some little dipole moment. Trans butene is absolutely 0. So cis has always a greater dipole moment than trans. And then we have, interestingly, the acid strength. You must remember very interesting aspect of acid strength. So this one, this dicarboxylic acid is bute 2 in dioic acid. E will be there. So this is cis, and this is called malic acid. This is famously called not cis malic. Malic acid is itself cis. Malic acid is stronger than its corresponding trans counterpart, the fumaric acid. This is the E part. This is the Z. This is the E, or the trans. So this is called the fumaric acid. And you will later know that malic acid can form its anhydride, because the carboxyl groups are lying on the same side. The dehydration between two carboxyl group is possible. So malic anhydride is a stable compound, but you cannot get a anhydride from the fumaric acid. Nobody will tell you a fumaric anhydride is non-existent, because the carboxyl groups are lying on the opposite side. Now, why I'm not talking about anhydride, I'm talking about the acid strength, why it is stronger, Now this, after having lost, because as we know that in a dicarboxylic acid or even dibasic acid, the acid strength, the pH, is all known from the first dissociation. The second dissociation is much, much less. So once it loses one proton, the conjugate base will be stabilized by, there will be an internal resonance here. I am not doing that. So due to intramolecular hydrogen bonding, intra-H bonding, that will stabilize the conjugate base. And therefore, the dissociation is more favored in conjugate base of malic acid. But such hydrogen bonding stabilization is not possible in fumaric acid. Not possible in the conjugate base of fumaric acid. So I am not writing the conjugate base of fumaric acid. You can understand the COH will remain on the other side, and once it loses a proton, it cannot hydrogen bond intramolecularly to stabilize itself. So the tendency for ionization is more in cis, that is malic acid is more acidic than fumaric acid. So that is a very interesting thing about the EZ ice, and I'll be showing you some more to save time. I forgot to tell you that a molecule can have a chiral center, can have a double bond. So this double bond is a stereoactive double bond, and this is a chiral center. So the number of isomers will be 2 to the power m plus n. N is the number of chiral center, m is the number of stereoactive double bonds. So this molecule here, the configuration, you have to write two version of the configuration. One in terms of R and S for chirality, and other in terms of E and Z for double bond diastereoisomerism. So this according to nomenclature, this will 1, 2, 3, 4. This will be 1, 2, 3. So this 3 is, you have to mention whether it is R or S. Because you are so very expert, you can rotate your eye from here, because hydrogen is lying on the below the plane. So OH, first look to OH, then this Buddha with a double bond, then ethyl with not a double bond. So it is going clockwise and it is R. So, or else you can convert it to a Fischer formula and do the same. So 3R, and the fourth position is a double bond. So hydrogen remaining on the same side. So also Buddha. So this is 3R 4Z, and the name X 4 in 3 all. And the total number of isomers stereoisomers from such a compound will be 4. R remaining fixed, 3R, 3R, it can be E and Z. SS remaining fixed, it can be E and Z. So 3R4Z, 3S4Z, 3R4E, 3S4E. So altogether there will be 4 diastereomers. All are diastereomers. No one is a mirror image. Because if one is different, then it cannot have mirror image. They are all diastereomers. Now, here you can just have a look. This molecule is a symmetrical molecule and N is equal to 3. So you have to apply the formula. N is odd, N minus 1 by 2. So you will find 6. You have to find out, calculate. You may not draw the different forms, but it will be 6. But the second one, 1, 2, 3, and unsymmetrical. So 2 to the power n, simply 8. I have just written Z, 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 E, Z, 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 E, Z, 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 E, 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 Z, Z, E, E, Z, E, and there are 8. So there is no need to write down, just there will be 8. And so also, I have given some examples where, there will be a pseudo-chiral center here. That is why I have written small r and small s. Just like R and S, if they are different, then the middle one is a pseudo-chiral center. Similarly, if this one will be E and this one will be Z, then the middle chiral center is a chiral center, is a pseudo-chiral center. If both are E or both are Z, then this is achiral. You understand what I say?
Yes, sir.
Yes, sir.
So in this way, you will find out which one. Supposing this molecule has only 2, because this vinyl is non-active, is inactive. Stereo inactive. This vinyl is stereo inactive. These are simply 2 vinyl groups. This is, stereoactive. I wrongly, I was trying to say stereoactive, optical active. This is stereoactive because this carbon is bonded to hydrogen and vinyl, and this carbon is bonded to hydrogen and allyl. So only one stereoactive double bond is there, so it will be only 2, Z and E. So must be very cautious, and this double bond is not stereoactive, only one. You understand?
Yes, sir.
This is an allene. Since I have changed the pattern, the sequence of teaching, therefore, and I've also told you, because you guys are very good, so I've told you there's accumulated double bond, having number of double bonds is 2, which is even, and the groups are different. It will not show geometrical isomerism because it will be a non-planar molecule. It will be showing D and L, right? So it will be 2. People do not know about chirality, different aspects of chirality, will say that it will be showing E and Z. No, it will not show E and Z. It will show enantiomerism. This is D and L. They are optically active. You understand? But if there are 3 cumulative double bonds, yes, it will show E and Z. Got it?
Yes, sir.
Yes, sir.
Yes, sir.
Now this answer is not for this one. It has come down for maybe this 0. That means it doesn't have any stereoisomers, because vinyl same, and they both are same. Then this is not a chiral center. If they would have been E and Z, then this would have been a chiral center. So there are, I have shown you the different possibilities. There can be one ZRE, and if you switch between the two, then it will be ZSE. And if the two are same, then it will be, this will be a chiral center. This, there will be no chiral, I'm so sorry. The middle one will vanish. It will be, as per ZZEE, there will be 2 forms. You understand? There will be 2 forms.
Yes, sir.
Because they're away from each other. So either, this methyl and an entire Buddha will remain opposite. So this will be Z, and the other one will be same, and this will be, or it will be EE. And the ZD and EZ, they are superimposed. I mean, I have not written ZD. Why? I'm discussing this question. So where this is not a chiral center, Yeah. Had it been JDE, then already you have discussed these two. Yes or no?
Yes, sir.
Had it been ZE, then we have another middle one entering into the configuration, making it a three-centered thing. So if both are either ZZ or EE, then middle one is not a chiral center. If middle one is a chiral center, means the other one is Z, the other one is E. And then you can have other, diastereomer by changing the middle chiral centers configuration. It will be smaller, converted to smallest. Got it?
Yes, sir.
Yes, sir.
Yes, sir.
Then, Miss Tripathi, you joined little late, right?
Yes, sir.
Okay, I have already discussed about, I have given you the example butane, the Z has a greater boiling point, 4 degree, and this is 1 degree. But melting point greater is that of E. Similar is the case with 1,2-dichloroethene. That is Z has a greater boiling point, C 60-48, and melting point -50. The E has a greater melting point. Dipole moment, if it is a symmetrical molecule, you will get 0 for the trans. It is unsymmetrical, but trans has a lower dipole moment. And this is 1.9 device, even greater than the dipole moment of water, which is 1.86. This is even butane has a residual, cis has a residual 0.33, and trans will be exactly 0. Acid strength I have already told about maleic and fumaric. Density and solubility. Yes, you will write later at home that E has a greater density than Z because the packing density always is taken in the solid state only. This generalization or approximate rule of thumb is applicable for the solid state. The E has a greater density than Z because of greater packing efficiency. While the solubility of Z is more because packing is strong, it doesn't dissolve easily. So it needs higher temperature. So at a particular temperature, the solubility of Z is more than E due to the same reason. And I have given examples. Malic acid, which is cis, has a density which is less than that of trans. But coming to the solubility in water, malic acid at 25 degrees Celsius is more soluble, 78.8 gram per 100 liter, while fumaric acid, the packing is so strong and the density is much higher, and therefore its solubility is much less, 0.7 gram per 100 ml at 25 degrees Celsius. Got it?
Yes, sir.
Yes, sir.
Yes, sir.
And the most important which we have done in our thermochemistry program, let me mention here the enthalpy of hydrogenation. Another point, or heat of hydrogenation. Always the trans E or trans here will be numerically less than that of Z because it is more stable. So the heat evolved. When I say heat evolved, the numeric value, I'm not taking the sign. The heat evolved, that means it is always del H is negative, but the numeric value will be always less for trans, which is more stable, less stable. As you know, that if some reactant is more stable, it has got a, this is trans butane, for example, this is more stable, but they will go to the same product. So the difference between these two will be more, or difference between these two will be more. Definitely, the product is the saturated compound, and therefore the numeric value of the heat of hydrogenation or heat of combustion will be less for trans, more for cis. Or in general, the one which is stable, maybe due to resonance or maybe due to any other reason, if it is stable, that its heat of hydrogenation, heat of combustion will be numerically less. Got it?
Yes, sir.
Yes, sir.
I have given you the value. Maybe one numeric value of E is nearly 1 kilocalories less than that of Z, butane. Now, while we are considering that of carbon-carbon double bond, it is worthwhile to discuss about the oximes, the GIs in aldoximes and ketoximes. You do not know what are oximes at this moment, doesn't matter, but I will tell you this is oximes. So this is supposing aldehyde. This is there is a double bond, and in place of double bond you get OH. So aldehydes and ketones, when they react with a compound called hydroxylamine, the chemical reaction produces this compound called oxime. So earlier, the nomenclature syn and anti, they were used. When hydrogen and OH, they are remaining on the other side, it was called anti. And you make a switch, these two must be different. You make a switch, then the OH and H will now go to the same side. In that case, oh, there is a lone pair. Sorry, nitrogen, I'm so sorry. This is CN double bond, not. Now hydrogen OH now has gone to the same side. This is called syn. But now these have been obsolete because E and Z has taken its. Similarly for ketoximes, so this will be, supposing methyl, this will be ethyl. So same, nitrogen will be there and there will be OH. One of the positions will be taken by the lone pair. So in this case, the same thing you have to do. This is number 1 group, this is number 2 group. So there is only one group which is taken as number 1 dash. So 1 and 1 dash, the remaining on the opposite side, so this will be E. E, whatever is the ketone, supposing butane 2-one oxime. So it has been prepared from butane 2-one, and it is not butane 2-one, it is its oxime. Similarly, this. Yes. Huh? Oh, what?
Sir, E will vanish.
Huh?
Sir, sir, naming sir 2ONE. Sir, E will vanish. Sir, oxime.
Huh?
Sir, in sir,
Your voice has gone terribly weird. कौन कहूला आउथरे कहला?
sir, E will be dropped.
Why? E कहेंगे drop होगा?
Sir, एठी O ରୁ ଆରମ୍ଭ ହଉଛି oxime ଟା.
हाँ?
Sir,
हाँ हाँ
O.
हाँ नहीं এইটা গোটে ইয়ে আইইউপিএসি কথা ମୁଁ କହୁନି, ଏଇଟା ତ ବିଟାନ୍ ଟ୍ୱନ୍ ଅକ୍ସିମ୍, এইটা ପଞ୍ଚ କରାଯାଏନି. So यार IUPAC nomenclature, if we are now curious to know se punch karuchi ki nahi, we can just have a diversion to. This has a different node. This is E, no doubt, OH and ethyl remaining in the opposite side E. And according to nomenclature, it is 2, 1, 2, 3, 4, butane, 2, illidine. So it is giving, I'm just writing its common name. Therefore, I did not drop E. But if you give a IUPAC name, it will be idene. So double bond is a bivalent group, butane, 2 ill. This is butane 2-ill, but since it is double bond, idene, extra idene is being suffixed, then it is hydroxylamine. So this will be treated as a hydroxylamine, right?
Okay, sir. Yes, sir.
So I have given you the simple name, but if you want an UPSC, nobody demands that. It will be you want two, so this group will be called butan 2-il. But since there's a double bond, it will be Ethene. And 1, 2, 2 position is stereoactive, so this will be 2E. Ethene, then the main compound is hydroxylamine. It was NH2 actually, but because of the reaction with the carbonyl compound, a double bond has been created. So this is the IUPAC name. So alu khodu khodu amaro eti saru baharla. Say anyway, that's one way better. So anyway, anybody who is watching from the YouTube, we are now in a great speed. So I'm sure those who are watching and will be watching in future will benefit if you are quite focused. No doubt about it. Well, but this one for the aldehyde, which we were calling, anti, but this will be number one, this will be number one, this will be actually Z. So anti is now Z. And this number one and number one, they will be opposite. This will be E. So therefore, anti-scene configuration, just I am showing you that supposing we'll make it symmetrical and aldehyde. It's not symmetrical. We'll make it an aldehyde. So particularly when there was HOH at that time, we'll make it H. And previous time there was terms applicable for these geometrical isomers for oximes. But now let me see what he is telling. It is, methyl number one and OH always is number one because there is one group. So this will be remaining on the same side, means Z. But previously OH, H were taken into consideration. It was told anti. So this will be ethylidene hydroxylamine. Obviously, why N-ethylidene? Because the ethylidene is bonded to N. I think in that also there was N, right?
Yes, sir.
Oh, so
Yes,
we forgot to mention that ethylidene is bonded to N. N is in the beginning. N not in the beginning. No, N is in the beginning. Then there will be a bracket that will be like this, right?
Yes, sir.
So the
So
yes,
the complex group will be get the bracket.
yeah. So this complex group has to be put inside this complex ethylidene group. That has to be put inside bracket. You have nicely pointed out. So the bracket will end here, right?
yes, sir.
Not
Yes, sir.
here. So remember this with all seriousness. Anti and sin, they are now out of the picture. EZ have come to the fore, and I have seen shown all these things. They are geometrical isomers. But if the two groups are same in ketoxims, then there will be no geometrical isomers. Now, similarly, you can have also in azo compounds, double bond N, double bond N, if the two groups are different, R dash are different. They can be cis and trans. Here, cis and trans can be used because there is only one group. If they are on the same side, then it is Z. If you found that they are on the opposite side, then it is trans. So as a compound, these are imines. Imines, there is one lone pair I have not shown. You have to make E and Z. Cis and trans will not be applicable. Just in place of NOH, in oxime there will be one OH. In place of one OH, there will be phenyl. Then it will be called imines or any other alkyl groups or aryl groups. It will be, and similarly hydrogens also, you will have the two groups are different, same principle as we studied for oximes will be applicable for unsymmetrical imines, hydrogens, phenyl hydrogens. like that. This is phenyl hydrazone. NH, then another pH. Similar type. Now, this is configurational stereoisomerism in cyclic compounds, which I have already told you to cover at the end. So, different types of cyclic compounds, and we'll show how R and S, configuration, both geometrical and optical will be studied together. First geometrical, and then we'll see that geometrical form has another enantiomer or not. We'll be seeing that. It's not today's agenda. So we complete geometrical isomerism. I'll say, give you the file. Then what was in our agenda next? Today's agenda was something different. I told you I told you that
Sir, there only, sir, you have written there, sir, conformational groups.
groups called conformational isomerism.
Yes,
Right?
sir, isomerism. Yes.
Yeah. Now we will be playing with dance steps. No bond breaking remaking. I deliberately have left the optical isomerism having chiral axis. Although I have sounded the allenes, substituted allenes, cumulative allenes which have even number of double bonds, which are optically active due to chiral axis. I have sounded you, but I will be doing that in official manner. I left it because one of the aspects of chiral axis is involving conformation. That is why it is worthwhile to study that at the end. Not at the very end, but before the wedding ceremony between configuration and conformation. I will be giving you the invite, and you can come with 2 guests to the ceremony. And we have in the first we'll have starter, and the main course will not be served. We'll be given starters, and then after 1 hour we will be opening the main course, and the starter program will be closed at that time. Or maybe after 2 hours, when the starter will be going down from your stomach and entering into your small intestine, at least to the half portion of the small intestine. Not large. Okay. Then let us change our mood, because we'll be dancing now. Although I have already hinted you the Newman and the Sawhorse projection formula, and I'm not going to introduce to you what is conformational isomerism, which we have already understood and written a few lines about it. So straightway we go to the conformation of ethane. The starting point of having a knowledge of conformation is this acyclic compound ethane. So let's draw both the Sawhorse projection formula. Where you get an eclipse conformation, H, 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 H. Let us, for the sake of understanding, make a mark here. Say, let us make it as HA. Just we are keeping track. What will happen when we rotate the carbon-carbon single bond? So let's rotate in a clockwise manner. You can as well rotate anti-clockwise. So if it 60-degree rotation, then you will get a stagger. This is eclipsed. And let us keep the front one fixed, and the rear one will be coming 60 degree, so that this angle, it was previously there like this. Now it is here. The HA is here with a dihedral angle of 60 degree. I told you the difference between the normal angle, which is a 2D angle, or dihedral angle is a 3D angle. So this is A. The dihedral angle is the angle between two planes. One plane, carrying HA, C1 and C2. The other plane carrying C1, C2 and HB. Supposing this is B. B is fixed. So this solid angle is called, now the angle is theta. So this theta is 60 degree now at this moment. So this is called the staggered form, which is the most stable form. Staggered form, which is a conformational isomer. I'll write then with a plus 60, that is a dihedral angle of 120 degree from the beginning. So this is phi 60, and this is plus 60 degree, means a dihedral angle from the beginning 120. So you will just draw the same eclipse form. The drawing should be exactly identical. Just like you draw a diagram of a frog or an eggplant or what we call brinjal, you do that. Then write where is HA, where is HB. You are not changing the front carbon. So HB is as usual. Now HA has come to this position with a dihedral angle from the beginning of another, this, it will come here, means dihedral angle will be 120 degree. This is eclipsed. And in a similar manner, if you have another 60 degree rotation in the same direction, the total dihedral angle from the beginning will be 180 degree. It will be getting, you'll be getting another, just draw. You must make a habit of drawing two forms in the conformation of acyclic compounds. Having two carbon atoms, you have to have two forms, eclipsed, staggered. Whether it is ethane or butane or whatever, propane, whatever, you will have only two types of, figures. This is up, so this will be down. This will be this side, this will be this side, this will be this side. So this is the staggered. But now the HA will be found at the bottom. These things you know. It's nothing new to you. This is again staggered, nothing different than this one. These two are identical in form. This is also staggered, not a different form. And another 60 degree with a total dihedral angle of 240, you will get another, eclipsed. Now the HA will be found. HB is always there at its position. We are not rotating it. I mean, we are not touching it. We are rotating the rear carbon. Therefore, HA will be found here with a dihedral angle of 240. And finally, with another 60 degree plus 60 with a total of 300, not finally, 300, you will be getting another, staggered form. Oh, sorry. Draw a staggered form as usual. Then the HA will be found here. This is another staggered form. Same. And finally, when you give another 60 degree rotation, a dihedral of 360 will reinstate the same form. I mean, the same eclipsed. Or eclipsed is always eclipsed, but another eclipsed. I mean, you come back to the starting position. if we draw graphically, done? Hello and
Yes, sir.
welcome those who
Yes,
are
sir.
watching from the YouTube. And let me, before we draw the energy profile, the energy diagram, let us go for the Newman projection formula, which is also handy. Newman, double N or single N? You have drawn?
Yes,
Yes.
sir.
Yes, sir.
And well, this is very handy. Just a circle, and this is the front carbon. Let us put it fixed. We can as well rotate this, but let us put the front carbon fixed, H. And the rear carbon is not visible. Just like it is a opaque circular disc, so that you are not able to observe the rear carbon while you are in the front. Therefore, it's you have to write like this. You cannot look exactly in the eclipsed situation, keeping yourself eclipsed with two hydrogens. So I used to say, Terigri no to what I used to say, funnily, so that you can draw. But actually they're eclipsed. Supposing this is HA, which will HB, and this is HA, which we will rotate now. This is eclipsed. I'm not writing one again and again eclipsed. Now 60 degree phi, 60, I'm writing in terms of phi. So the other form will be exactly this. So we'll be alternating between the staggered and eclipse form. Same diagram will be repeating again and again. So HA will be now moving. This is our wish now. We could have also moved HB. So B is, we have kept static, and this, the dihedral angle is clearly visible, is a solid angle. Now with another 60 degree, let us write phi is equal to now this, instead of writing here, we write phi is equal to 60 degree here, and then we don't write anything over the arrow mark. Instead, we draw another eclipsed, unda. I used to say unda. Undantini. I forgot the real funny word that I often use is unda. So you draw the eclipse form by unding. In Odia, I'm talking those who are non-Odia guys, and undi you can't understand. It's just क्या हिंदी में क्या होगा इसका क्रूड जो उंडी बारे उंडू च कौन मते सो उंडी की टिके देखिବାକୁ ପଡିବ सो पुणी उंडा फॉर्म आसीगला. First you draw H, then see what has happened to the fate of A. So undoubtedly A has come here. This is another same eclipse form has regenerated with phi. Just write down below phi is equal to 120. Then you draw staggered format. You know, staggered format is fixed. The drawing is fixed. Only one staggered and eclipse. Only these two. These are the two. One is stable, the other one is unstable. There is nothing third. But there can be more than one staggered forms, which are not called staggered. As we continue to have substitution, staggered word will be replaced by anti and some other Gauche, anti, different words will come. But form is staggered format, I used to say. The only two formats there, one is eclipse format, which is really non-existent. It is rotating in such a rapid rate. Unless there is a bulky group, then you can't expect at a given moment more than a couple of molecules, or maybe few molecules will be found in the eclipse form. 99.9% of the molecules will be found in the staggered form. So this, you will find that this this HA has come here, SB is static. Now this is phi is equal to 180 degree, another staggered. Similarly, we can draw, I'm just doing deliberately to make you acquainted with the Unda and the staggered format. Must be very prompt at drawing the Unda format for eclipsed and the staggered format for stable one. And now HA has come to this position, HB as usual. So this is phi is equal to 240. And then we have another staggered format where we have HA has gone to this position. Well, so this is phi is equal to 300. And finally, another 60 degree where the total dihedral angle is, you can just get another Unda form. So there is repetition of the original form. I mean, no doubt it is same eclipse, sorry. So let's talk these things in terms of graph. Drawn?
Yes, sir.
Yes, sir.
Yes, sir.
Now, graphically, let me tell you one H. Before that, let us write down why eclipse form conformation is unstable due to maximum what we call torsional strain. I'll be introducing different forms of strain, including mental strain that all of us are having once our dream or our health becomes bad or our dream is not going to be fulfilled, then we become mentally strained. So that is another strain. But this is a molecular strain. This is called torsional strain, or sometimes it is called the bond opposition strain. That when this is the repulsion between adjacent bonding electrons. It is not steric. It is not due to the atoms and groups. It is due to the bonds remaining close to each other. The more it comes closer, and finally the closest is the eclipse conformation, where the three pairs of hydrogen will come in line in eclipse. So that will have the highest torsional strain or bond opposition strain. That is why it is the most unstable. And the staggered has the least, you can call it conformer or rotamer. The one which is a stable one, you can use the word conformer or rotamer. This is a conformational conformation, not even isomer. Conformer means conformational isomer, which really exists. But eclipsed is simply a conformation via which it rotates. Now has least torsional strain, because the three pairs, they're opposite to each other. Of course, this one has come 60 degree apart, but this has gone opposite to the other one. This has gone opposite to the other one. You will discover three pairs of hydrogens remaining opposite. The 1 degree less or 1 degree more will make the bonds coming closer. Only at when we give 60 degree turn, it will be either going from more stable to least stable, eclipsed, or next 60 degree will go from the least stable to more stable, heading towards more stability. There is as you proceed from eclipsed slowly to staggered, stability will go on increasing till the torsional strain is minimum in the staggered. Again, from going from staggered to eclipsed, you will find the torsional strain will build up more and will be maximum in the eclipsed conformation. Got it?
Yes, sir.
Yes, sir.
Yes, sir.
And if we draw the energy profile, this actually, some people like potential energy. Actually, it is G. It's free energy, actually. This has taken the entropy factor into consideration. Very less people are aware of it. In the book, you will find potential energy. It's what potential energy? It's free energy. And now you'll find that if we start from here, from the eclipsed one, will be going very symmetrically up and down in 360-degree. You'll find 3 humps and 3 crests and 3 trumps. So this is the most stable form where I'm just drawing to show you. This is staggered form. This is the eclipse form. I'm drawing here to show the Unda form, eclipsed, this is staggered. Again, this is phi, this is 0. This is phi versus free energy. And here, this will be again an eclipse form at, this is 60-degree. This is 120-degree. You will get another eclipse form. This is 180-degree. You will get again staggered. I'm so sorry. Staggered. Then another, this is 240. You will get a eclipse form, and 300. This will be a staggered form, and finally you will arrive at the same. This line is one line. Although my drawing is very, 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 very erratic, so you will get at oh my God. Oh my God. What is happening? Right? So this is what we call the difference between staggered and anti is quite low. It is about 3 kilocalories per mole. Actually 2.9 something. So we say 3 kilocalories per mole. And one HH eclipsed, H dot 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 H eclipsed costs about 1 kilocalories per mole. Remember this, distribution. If there are 3 pairs which are coming eclipse, for 1 pair 1, so 3 pairs 3. In this way, you can calculate in some other molecules, other conformations, how much the interaction energy, is. So if we consider this as 0, these are opposite, these two are opposite, these two are opposite. So relatively, this will have 1. So the difference between the staggered and this is 3. And 3 kilocalories is, is not much. It is less to the extent that the rotation is very rapid. I will show you 10 to the power some whooping 10 to the power 40 or something times a rotation occurs in 1 second. And then at a given point of time, you'll find 99.9% of the molecules in this staggered form. So at this time, I would like you to show you the file and you can understand. So you see, this we have already done. About 3 kilocalories, because one pair has 1. Somewhere I have written one. This is the dihedral angle I have shown between 2 planes. And yeah, somewhere I have written 1. Yeah, At 25 degrees Celsius, I'm sorry. At 25 degree, I mean, room temperature, there are 5 times 10 to the power 6 revolutions or rotations per second. And at any instant, the staggered form contributes 99.9%. And the rest 0.1% remains in other conformations, not eclipsed. I mean, in between eclipsed and EE. Lowering the temperature, reduces the rate of rotation, and the percentage of staggered form further increases. And increasing the temperature, you will find rotation further increases, so that the percentage of conformations in other than staggered will be little more at 0.1 से थोड़ा सा ज्यादा हो जाएगा. लेकिन the dominant contribution will be staggered. So this and the other things which I have given you, and these are the E. Actually, it is Z. The energy means it is Z, because we'll be calculating the equilibrium constant directly from delta Z. I'll just here 1 kilocalorie for one hydrogen. I mean, not bonded, eclipsed. This I must write interaction. Hence, approximately 3. Now, let's go for higher alkanes. Butane, will bring about 2 stable staggered formants. So, staggered word will be replaced. Now, let's straight away go from for the Newman projection. And I will give you a home task to draw a similar type of, that you have done in ethane in the Sawhurst projection formula. Now, the only difference here you find, as I have already mentioned, that this Unda form, this will be CH3, and this will be another CH3. And that contains 3 hydrogen atoms. I'm not showing, I'm condensing it. I'm showing the 2 middle carbon atoms to understand the conformational changes more, convincingly. So I have not putting H. So that will look little weird. So I have made it CH3, and others are H. So only the 2 middle carbon atoms are taken, and this is eclipsed. And this eclipsed one, I say, this is many people call sin. To distinguish between eclipse 2, which is only called eclipsed. So this is the most unstable. Here, besides, the bond opposition strain, which is maximum, you will find another strain coming is the steric strain. But there will be, other than hydrogen, a methyl, which has an umbrella of sp3. So the entire electron cloud of the methyl groups, they are coming close to each other. So in this space, they will repel. So any interaction, repulsion between the 2 groups, not hydrogen will not have a spatial effect. Only other groups which will be coming close, there will be repulsion in this space. So whenever a bulky group comes nearer to each other, then there will be a steric repulsion. This is called a van der Waals strain or steric strain. I will write down that later. So this is called eclipsed 1, which is most unstable. And I remember, we'll just see how far my memory is correct. One methyl interaction, apart from the bond opposition strain, which is 1, the other one and the van der Waals strain, कुल मिला के मुझे लगता है 2.9 or 2.7 kilocalories will be, and hydrogen will have only bond opposition strain 1 plus 1 plus 2.7, it will be quite large. I will tell you whether it is 2 point something or 3 point something. I'll tell you. So this is the most unstable. I will write down that. Then make 60-degree rotation. So this is, say, phi is equal to 0 degree. And supposing this will be bringing, keeping the front one as usual, Then staggered format. The only two formats you should be acquainted is the staggered and eclipse. This is a staggered format. So the front methyl will remain in the same position, but the rear methyl will come here with a dihedral angle of 60 degree. Phi is equal to 60. So this here, when the methyl are at a dihedral angle of 60 degree apart, this staggered form is not called staggered, it's called Gauche. This is a stable form, not most stable, stable form. In fact, molecules, butane molecules exist in about 20% in the room temperature, in about 20% in the Gauche form. It is a staggered format. Here, there will be only some steric strain because methyl groups are not exactly eclipsed. They are away from each other, but still they are 60 degree apart. There will be some steric strain, but no bond opposition strain because this bond, opposite. This bond, opposite. This bond, this bond. So no bond opposition strain, but there will be some steric strain, and therefore it will not be the most stable conformation. I will tell you. Then another 60 degree will make it an eclipse form once again, but this eclipse and that eclipse will be different. So draw the eclipse format, the Unda format that I have told you, the Unda format you draw. So the first methyl will remain as in its position and the second rear methyl will now come here. I'm just rounding it off just to show you. I'm not rounding this one, but rounding the one which is rotating and changing position. So this is eclipsed 2, and this is really called eclipsed by many people. That is called sin, which is unstable, less unstable. Unstable because there will be bond opposition strain, maximum bond opposition strain, and some little bit of steric strain because hydrogen is a very tiny atom. Methyl will be having some spread of legs and head, so there will be some little steric strain. So it's not like HH, ethane says zarur unstable hai. Ethane eclipse hai, little more unstable because of methyl coming into picture, taking the place of hydrogen, but it is the real eclipse form. I mean, this is called the eclipse form, but that is called the scene form. Then giving this is dihedral angle of 120. Then finally, when you give another 60 degree rotation, you get a staggered format. Then what happens to the methyl? Methyl now comes opposite to this methyl. And this is another staggered form called the antiform, which is the most stable form. And this is more stable than the staggered form, Gauche form by only 0.9 kilocalories, less than 1 kilocalories. And therefore, the difference, I'm talking of the difference. And therefore, since the energy difference is so small that delta G is so small that we will calculate the equilibrium constant at room temperature. About 82% remains in the anti and remaining 18% remain in Gauche. Gauche is a stable form. And then this is phi is equal to 180 degree where you get anti. And again another 60 degree will make it eclipsed, like eclipsed 2. But it will be in the opposite side. I mean, this first you draw the Unda format, as much Unda as possible, but not a weird Unda that the Unda will look like a Gunda. I mean, staggered. So, so this is like eclipsed, the energy wise it is eclipsed 2, but I will ask you, what is the relationship between the two? We will eclipse 2, that is eclipsed, right? These eclipse conformations are non-existent, just theoretically we are looking. So this is phi is equal to 240. And then another 60 degree, we will get the other Gauche where this methyl will be coming to the left side of the first methyl. And this is another Gauche. This is also Gauche energy same. Then I will ask you, this is supposing Gauche 2, this is Gauche 1. But energy wise they are same. GAU CHE Gauche. No, GAU C. Yeah, CHE. Okay. Now finally, this is a dihedral angle of 300, and finally you back to the first Unda form, what we call the scene form. Same as 0, phi is equal to 0. Now have you drawn this?
Yes, sir.
Yes, sir.
Yes, sir.
Homework is to draw the Sawhorse projection. This is very simple, just like this. These are the two. This is the this Unda is not here. CS3 will be here. This is starting from the scene form, eclipsed 1, and then you continue to get the same, draw the staggered format, but name staggered will not be there. It will be first Gauche, then eclipse 2, then anti, then eclipse 2, similar to eclipse 2, and then another Gauche, then finally back to Pavilion. You draw this at home. Now my question is, before we enter into the energy dynamics, we consider two things. One, this Gauche and this Gauche, are they identical? Are they superimposable or not? They're the same, identical ones or not? What you feel like? And what about this eclipsed 2 here? This is eclipse 2. This is another eclipse 2. Eclipse 2 in phi 120. This is another eclipse 2 in phi 240. So how they are related, or are they identical? First talk about Gauss.
Sir, they are mirror images, non-superimposable.
What you say, Mr. Pati? Same, or you are not able to make out?
Sir, can you please repeat the question?
Question is the Gauss one, where the methyl is on the right side. Another Gauss is at methyl in the left side, here. These are two Gauss forms. But are they identical? Although I have told energetically they are identical, are they really identical? Or as Rudra said, they are not identical, they are their mirror images. They are not superimposable. What do you say?
Sir, not identical.
They are superimposable, right? They are mirror images, right?
Yes, sir.
Omkar, what do you say?
Yes, sir. Mirror images.
Precisely, Ansul, they are not identical, they are mirror images. Here comes the very first concept of the conformational enantiotropism. They are conformations, but they are enantiomers. And somebody will ask you, what is the cause? The cause is the presence of chiral axis with respect to a axis, molecular axis. This is dissymmetric because it has got another mirror image form, which are not superimposable. If I make two things, one Gauss keeping as such, and another model I will change to the other Gauss to the left side, you cannot superimpose. They are different. They are conformations, conformers, they are also enantiomers. The question is, the people will laugh at you when you say there is one optical isomer in N-butane. They will find for Tara. They will not find any Tara here. So you will say it is optical inactive molecule. I asked, once I went to select a teacher, a postgraduate teacher for class 11 and 12 and plus 2 in a DAV Chandrasekharpur, Bhubaneswar, talking of about maybe 6-7 years before. So I asked a question to a potential teacher, 3-4 of them could not visualize what I am asking. But the one guy, I will not name, he was appointed immediately. He answered correctly. Say they are not same, they are superimposable. Then I asked why then N-butane is having a form Gauche, which is optically active. What is the cause? Is there any chiral center? Immediately say, no, there is a chiral axis. Then again, my next question, my follow-up question was, then why then optical activity is not seen in N-butane? It is because the rotation, the rotation is so rapid that they are inseparable reciprocity. You can never ever separate between the two Gauss forms. They are remaining in 50-50, energetically same. There, the rotation is so rapid that you can't separate them. That is why the optical activity is not seen. But the first example of conformations which are also enantiomers is this N-butane, a Gauss form, not anti. Tell me another question to you, why anti-form is optically inactive? A Gauss form is optically active because there is a chiral axis. It is dissymmetric. But why anti-form is optically inactive?
Sir, center of symmetry.
Yes, there is an inversion center. If you look to the carbon-carbon middle point, then if you draw lines, then this methyl, they will touch in one line. So they are opposite to each other. I hope you understand. I need not have to show the model. I'm saving time, not showing you the model because I am not handling guys who are out of focus. You understand?
Yes, sir.
So there is a I, sigma is absent here. This is I. Because of the presence of inversion center, this is optically inactive. And what about the eclipse, which is a non-entity? This eclipse, first one, the scene. Although it is hypothetical, it's very, very energetically high, then why? Why it is optically inactive?
Sir, plane of symmetry.
There is a plane of symmetry. But these two, they are also mirror images. This eclipse 2 and this eclipse 2, they are also mirror images. But since this is also due to chiral axis, but since these are non-existent, a question of Gauss is a point of discussion because they exist. But this eclipse forms, they do not exist. But theoretically, yes, they are mirror images too. They are non-superimposable mirror images. You got it?
Yes, sir.
Now, coming to this time, I'm sorry. Let me write down Gauss form is a chiral due to chiral axis. Gauss 1 and Gauss 2 are enantiomers. Inseparable racemate. You can't separate them because the barrier to rotation is so low that you can't separate them. But yes, theoretically, they are enantiomers. Maybe in a higher level program, I might have told, I could have told you that at a sufficient low temperature, where you go sub-zero, below that, close to nitrogen's boiling temperature and say oxygen's boiling temperature and all that, you may find that the two forms, the rotation becomes so frozen, even if it is a single bond, that rotation becomes so frozen that you may be able to separate the Gauche 1 from Gauche 2. But that is not possible in the gaseous form because N-butene is a gas, which is at room temperature. It's a gas. But at low temperature, it can be liquid, can be solid. So it can be possible. It's not impossible. Theoretically, it is possible. So practically also can be possible in such cases. You have to go to very, very low temperature. Now, graph. It's very interesting when you give the graph of G, some right E, so you will be find there will be one line here, the other line here, because unless we create, and there will be another two lines. So that you can draw very easily. So start from the same form, then come to the first form, that is Gauche, and then go to the eclipse 2, then come to the antiform here, then go again to the Gauche, eclipse 2 type, then come to another Gauche here, and then go to this is Gauche, then go to finally this is 60, this is 120, this is 180 anti, this is 240, this is 300 is Gauche, and finally go to the highest form here. And this energy difference between this is Gauche 1, this is Gauche 2, there is only one anti-form, anti, this is eclipsed 1, eclipse 2, I call it scene, and this is same as scene. This is eclipse, actually this is eclipse 2. And this is eclipse 2. As I told you, this is 2 and 2 dash. They are mirror images, but they're unstable. And this is scene coming back to the same scene. Right? And the energy difference between the scene and anti, this is very, very low. 0.9 kilocalories. So antiform is more stable than Gauche form by 0.9 kilocalories per mole, or del G is equal to minus 0.9. This conversion, when we talk of, Gauche to anti. Anti has a lower energy, and we can find the equilibrium constant because del G naught is given here. So we can find out what is the percentage of anti. Equilibrium constant will be more than 1. So you will know that. Numerically, it is 0.9 kilocalories per mole. But when you write this equation, Gauche to anti, anti has a lower energy. So lower minus higher will be negative. And now, you find the energy gap between this is quite high. This energy gap between this and this about 5. I will give you fill up that. I am now showing you, but before that, let me write down why eclipsed 1 is most unstable. Seen, as some people call, is most unstable because of 2 reasons. What? Who can tell me? Maximum torsional strain, that is common. That is common to any eclipsed conformation, and the additional strain that it is having, maximum what? Steric strain or van der Waals strain between methyl groups in space. And why the antiform is more stable? More stable because least torsional strain and least what?
Steric strain.
Because they're opposite. The methyl groups are opposite. Then why Gauche form is a little Gauche form is stable but not more stable, has no torsional strain. No torsional strain, but some
Steric strain.
some steric strain, not high, because they are 60 degree apart. Some steric strain is there. So So Gauche and anti, that separation is 0.9 kilocalories per mole. Got it?
Yes, sir.
Now, I will show you some calculations here. Are you feeling hungry? So you are in a dilemma whether to tell the truth or to tell a lie. Tell something which will neither be wrong, neither be a lie, and neither you will displease me. Saying that yes, we are hungry, but we are interested to continue. That's it. And I will say sometimes hunger is good. There are two types of hunger. One is the mental hunger, and the other one is the physical hunger. When really body needs it. Sometimes we can't distinguish because we are so foodie. Sometimes our mental hunger outweighs the actual physical hunger. We eat whatever we see, we eat, and we gain weight, and we become disfigured. Well, I'm showing you some of the calculations. So this graph, I have already told you the sin, eclipse 2, same, but they're mirror images, anti, Gauss, and about 5 kilocalories. This from the very start, the energy, absolute energy, not del G. G. I have written everything that here I have given a table here. Delta G between Gauss and anti is 0.9 kilocalories. Delta G between sine and Gauss, the sine, the most, and the Gauss is 3.7. Delta Z between sine and anti, the highest difference is 4.6. Delta Z between eclipsed, that means eclipse 2, and anti is 3.8. And this is 4.6. So the difference between sine and eclipse is 0.8. So we don't bother about this. This is important. And therefore, between 2-methyl, yes, it is 2 points. I was telling 2.7. It is 2.6. And for hydrogen 1, so the total interaction energy, if we compare between anti and this one, anti taken as 0, the interaction energy will be 4.6, 1 plus 1 plus 2.6. And hydrogen methyl will be 1.4. So 0.4 extra is due to steric. Some steric because methyl has its limbs, protruded outside, which will also have a steric influence on the hydrogen's electron, steric influence. So it is 1.4 between methyl hydrogen. So the interaction energy is less. This is more by about this is 1.4, 1.4, 2.8 plus 1, 3.8. And this will be 4.6. So all these, I have given you the data where you find this. But the most interesting part is the calculation. Calculate between this, what percentage of anti and Gauss will remain at 25 degrees Celsius. If you keep 298 and apply the thermodynamics principle, you get K is equal to 4.5. That means 25 degrees C, 82% will anti and 18% will be Gauss in equilibrium. But with increase in temperature, undoubtedly K value will be reduced, no doubt. If the temperature is increased, the K value will be reduced. But you can never go below 1. It will always remain above 1. So people think that some temperature, the percentage of Gauss will be more. In some books, you will find that at higher temperature, Gauss will be predominant than anti. It's never ever the case. Mathematically also you will find even at 700 Kelvin, that is 298, 700. So 500 Kelvin, 500 degree higher, the percentage of anti has reduced from 82 to only 74 and 18 has increased to 26. So whatever may be the high temperature, the percentage of anti can never go below 50. Conversely, the percentage of Gauche can never exceed 50. And this is the example I have shown you. At 700, the percentage has only risen 8%.
Palado.
Hmm? What? Who is telling? Anyone?
No, sir.
कार ଗୋଟେ ଖୋଲିଗଲା नहीं
Sir,
कार
answer.
okay so you can mathematically check that this minus will be plus, and at 25 to 98 it is coming 4.5. You can take any value, you will not get less than 1. If it is less than 1, it will go and Gauss will be more, but it will never ever come less than 1. So that, that is a misnomer, that at a very high temperature it will go above, the Gauss will go above 50%. No. So I think we will close today's session, not because you are reluctant, but because I am tired. So in the next program, we will see conformation of a similar type of compound, 1,2-dichloro, where another strain will be introduced. That is called the dipolar strain, because it is convincingly a negative pole. Negative pole, they will repel electrostatically. The whole electron cloud will repel in space, that is steric. But the negative pole, the static electricity, same pole, same charge repel, that is another strain that will be added to the molecule, that is called the dipolar strain. So all these things we will know, then we'll know a typical case of ethylene glycol. You can understand once I tell you, but we will write. Ethylene, the Gauss form is more stable than antiform in nonpolar solvent, particularly because of intramolecular hydrogen bonding. That will make the Gauss form more stable than anti. But once you put water, polar solvent, then due to hydrogen bonding interaction, the antiform will be more stable than Gauss as usual. They will take all molecules from, almost many molecules from Gauss to anti because of water. So these things we will write. And higher alkanes, there will be zigzag conformation. All trans or zigzag conformation is the most stable conformation for higher alkanes. We'll talk about that very, you will write down these things at home, the difference of energy level, and this calculation also you will be doing at home, and also this point. And this you may or you may not, because we'll be doing tomorrow. Any question? I think we have almost completed our plan, is it?
Yes, sir.
Acyclic, I have never ever said cyclic. Cyclohexane is another class. That I can punch with, I think we are coming very close. The wedding ceremony will be in the last class. And let me tell you that today is Friday, and Monday will be the wedding ceremony. And so you come with your siblings to join the ceremony. First take the starter, and then, since you are not adults, so there will be also bar, like in US you go to any party, they call party, you will find there will be a bar everywhere. It's very common, nobody will shy away. Even the children, they know, they never bother. They know that when we will be 18 plus, then we will be taking wine or champagne with our parents, not in a clandestine way as is done in countries like ours, where we hide many things, our bad habits, or maybe some habits. I don't say, I don't judge from parents, but the Western people, they're one way different from ours. Even the children, they know. We are sitting in the same table. But parents can take wine, but we won't. They never grumble or never hesitate. So there will be there, but since you are not 18, so you'll not be allowed to touch, even if there is a bar. But you'll be taking a lot of starters. But look, listen to your physical hunger. Don't listen to your mental hunger, which is very deceptive. It's very deceptive. Bye-bye. Bye. Those who are watching, Asa, by the way, can we not sit tomorrow at the same time?
Yes, sir. We can sit, sir.
Mr. Patil?
Yes, sir. We can sit.
Yes, I understand. Ansul, you have some coaching, and maybe Omkar is not very sure, but you can watch later. You can watch later.
No, sir. Maybe I can sit. Yes, sir. I can sit tomorrow.
What? Omkar?
Yes, sir. I can sit tomorrow. I
Yes,
think.
Omkar can sit tomorrow, but I know.
Sir, I also can sit.
Okay. So I'll be, soon scheduling tomorrow's class because we'll wind up and start GOC. And also at the end, I will give you the entire file which contains all the stereoisomerism questions separated from GCOC where you will answer. Bye-bye. And those who are watching, this human greed, I have not monetized my channel and I will never monetize. But still, if the subscribers number is more, it is really rewarding and feel good factor will definitely be more. So if you have not subscribed to my channel, then you can consider subscribing to my channel. Bye-bye. See you tomorrow at the same time, 6:30. Yes.